Morning, folks. I'm going to go ahead and make a video so that we can hopefully get through this class, maybe even a little bit quicker today. So I'm supposed to be covering section 6.3 and 6.4. So let's go ahead and get started in section 6.3. From your video, you had switching back and forth between exponential form and logarithmic form. I'm not going to go back through that. Let's just go ahead and put it into practice. The big deal here is that these guys are undo buttons of each other. An exponential is undone by a logarithm. Logarithm is undone by an exponential. So the first four questions are questions that there's no math involved. This is just a conversion. So you'll notice that examples 1 and 2, these guys are exponentials. We want to turn them into logarithms. And I want to use this little graphic here. This is not mine. I stole this off of Pinterest. But let's use this graphic to be able to do that. So this is an exponential. I want to turn it into a logarithm. And so I'm going to use my L concept to be able to turn it into a logarithm. So this is going to be written as log base 2 of 32 is equal to 5. Now, just a couple of comments on this. I want you to notice that these three things are all written. If we were typing them, they would all be in the same font. They would all be in the same size. They would all be on the same line. So just understand they're all exactly the same line, same size. The only thing that's written differently is the 2, and this is written as a subscript. So just understand that the way that you write this is very important. All right, then let's head over to example 2. Same concept here. Let's use our L for this. So we're going to have the log of base 2/3. That's the only thing written as a subscript. The log base 2/3 of 27/8. Notice that's the same size on the same sign on the same line as the logarithm is equal to -3. Now let's go backwards. This is where we want to take a logarithm and turn it into an exponential, and we'll use the E to do this. So we're going to start with the base of 4. We'll raise that to the -3rd power, and that's going to equal 1/64. And then for example 4, same thing. We'll start with the base of 3, raise that to the 2/3 power, and that's going to equal the cubed root of 9. Again, there's no math involved in either one of those. It's just simply converting from one type of mathematical statement to another type of mathematical statement. We had special logarithms. Special logarithms, common logarithm is the base of 10, and the natural logarithm is the base of E. So just take note of how the proper way to write them would be. And then I believe this was your embedded question. So embedded questions should already be turned in by now. But if you did this on the embedded question, log base A of 1 is equal to what? And you can think of that, I said this in the video, you can think of that as A to what power is equal to 1. And we know then that that is A to the 0 power is equal to 1. When you go over to example number 2, or let me finish this up, sorry, under example number 1 or property number 1, the way that we say this is that any log of 1 is equal to 0. Just like in the last section, we said that whenever I take a base and raise it to a 0 power, I always get 1. All right, now let's go to property number 2. Property number 2 says that log base A of A to the X is equal to what? So when you're thinking of this, A to what power is equal to A to the X? Well, your bases are already like, so your powers have to be alike. So we're just missing an X there. And the way that I like to talk about this one is that when my bases are alike, remember that logs and exponentials undo each other. So this only happens when your bases are alike. So when you undo those two, you get the X alone. Same concept with number 3 property. Again, you've got a logarithm. but your logarithm is your exponent. So again, notice that they have the same base. They both have a base of a, and so they're undoing each other. So we would say then that these are, this is equal to 5. Now, if I wanted to put that into practice, let me see if I can show these both at the same time. If I want to put that into practice, the natural log of 1, we're going to be using here any log of 1 is equal to 0. It doesn't matter what kind of log it is. So any log of 1 is equal to 0. For example number 6, is like property number 3. Notice that these two have the same base. This is e raised to, remember that ln of x is the same as log base e. So this really says e raised to the log base e of x. So that's the property that we're looking at. So this is going to equal x. And then the last one, number 7, is going to be like property number 2. Notice that there's no base written here. No base says that this is an automatic base 10. So really number 7 says log base 10 of 10 to the -4th. So you're looking at something like this, log base 10 of 10 to the -4th is going to be -4. Now let's solve an equation. We know that solve an equation means go find out what's missing, or in this case, sometimes it's go find the variable. So let's use exponentials to do this. All right, so we have 3 raised to the x power is equal to 81. Now, when you see it written like this isn't any different than what we did in class, last class period. So we want to get our bases alike, and then we can solve for that power. So leave the left side alone. When I get my base alike, this is going to be 3 to the 4th power. 81 is the same thing as 3 to the 4th power. So now we can set up the mini equation, x is equal to 4, and we solved for x. For number 9, there's no x, but we can put one in there if we want to. We can say that this is x. If I were to see this, though, I probably wouldn't have written it like this. I only wrote it like this because the textbook wrote it like this. I probably would have written this as log of 0.01 equals x, because a base of 10 doesn't need to have the base written. The next thing I want you to realize is that if you were to think of this as reading it properly, we wouldn't read it 0.01. We would read this as 1/100th. And so my brain would say, oh, well, 1/100th actually looks like a fraction. And 1/100th is the same thing. Let's use our exponential rules that we talked about last class period. You might want to have those open in front of you. Is the same thing as 10 to the -2nd power. We know that 10 squared is 100. If we want to put top, that's going to be 10 to the -2nd power. Well, now all of a sudden, notice that my bases are alike. And so when my bases are alike, the powers and the logarithms undo each other. So my x then is just equal to -2. And a lot of this, folks, can be done mentally. It doesn't necessarily have to be written down. I just wanted to show you what my brain was doing there. All right, same concept with this one. We've got log base 3. I would rewrite this as 3 to the -1st power. And I can use property number 2 to do that. So since my bases are alike, my answer is just going to be the power. Number 11, any log of 1 is equal to 0. And for the record, I would not have written it like this. I would have written it as ln of 1, because log base e is the same thing as the natural log. Number 12. Remember that in the last section, we learned how to change our roots into fraction powers. That was rule number 8. So again, if you've got your exponent rules out in front of you, you can see rule number 8. And so I'm going to rewrite my square root as a fraction power. So that'll be log base 6 of 6 to the 1/2 power. Remember, the root number goes on the bottom and the power number goes on the top. So this is to the first power, so my 1 is on top, but this is a square root. Well, now that bases are alike, I know that I'm just going to equal my power. Again, let's get our bases alike on this one. So we have log base 3. Let's change our 27 into 3 cubed. That's the same thing as 27. And don't forget, we still have the 3/2 power. Now let's clean this up a little bit before we decide what it equals. We know that from the last section, when you raise a power to a power, you multiply your powers. So this is going to be 3 to the 3/1 times 3/2. So that's going to be 9/2. Well, now that my bases are alike, I know that I'm just left with the power, which is 9/2. All right, number 14, let's use those exponential rules here. Let's turn it into an exponential. So we have x to the 6th power is equal to 5 to the 2nd power. Now, the goal is to get x alone. And so you could take the 6th root of both sides. Don't write this down because I'm going to erase it. I could take the 6th root of both sides, but the 6th root is the same thing as raising to the 1/6 power. So that's what I'm going to do. I'm going to raise both sides to the 1/6 power. So when you raise a power to a power, multiply your powers. That tells me that these two are going to cancel each other out. So this is going to be x to the 1st. I don't need to write to the 1st. And on the other side, when you raise a power to a power, 2/1 times 1/6 is going to be 5 to the 1/3 power. 2/6 reduces to 1/3. I have my x alone, so I'm finished with that question. When you look at number 15, let's do the exact same thing. So I have 4 raised to the negative 1/6 power is equal to x. Folks, the goal was to solve for x. The goal was to get x alone. I just did that. So this is totally fine as an answer. There are several other ways you could write this answer. I'll do this over to the side. If x is equal to 4 to the negative 1/6, this is the same thing as 1/4 to the positive 1/6. This is the same thing as 1/6 root of 4. But then that makes me have a root on bottom, and we know that that's not simplified. So honestly, I would leave it the way that we found it in the first place. But just understand there are multiple ways of writing the same thing. All right, a little more of the same, evaluate without a calculator. Notice that number 16 actually has a base of 10. We just don't need to write it. So since the bases are alike, I know my answer is 4.3. Number 17, let me move this over a little bit. It got shifted in the last update. Again, I know that this is log base e of e to the 0.5. We just don't write it like that. So since the bases are alike, I know that my answer is 0.5. Number 18, sorry, this is number 18 here. So number 18, we have the square root of 2. I'm just copying that for a minute. I'm not going to mess with it. But notice that on this next piece, I have natural log of e. This is log base e of e to the root 2 power. Well, log base e of e, they're going to undo each other, leaving me with just the root 2 for the second piece. So literally, I'm looking at these two pieces. This guy goes here, and this whole guy goes here. Well, root 2 times root 2 is just a 2. All right, now we have to evaluate with a calculator. So go ahead and pull your calculator out. And you'll notice that on the left side of the calculator, you've got a log button and you also have an ln button. The log button is a log base 10. The ln button is a log base e. So you have your common and your natural logs right there on the calculator. So for this first one, number 19, you have the log. So just push the log button. and then type in 1247, push enter. And you should get in here, let's round to the nearest hundredth. And so you have a 3 point, it says 0.95. It's actually 0.95866 yada yada yada. Well, this is my nearest hundredth. That 5 is going to make me go up, so this is going to be then 3.10. For number 20, let's do the same thing. Just push your natural log button and then 0.014. And on this one, you should get negative 4.268697,949. So if we're rounding to the nearest hundredth, this is going to become negative 4.27. So then we have some more properties of logarithms. These are going to be used to expand a logarithm or to condense a logarithm. So just understand that these two words, expanding and condensing, I'm going to use pretty faithfully when we get to questions like this. These are the rules that we'll use for expanding and condensing. So for the first product rule, you've already written it down from the video notes or notes video. And so when you have the log of a product, so notice here's the log, and I'm taking the log of a product, two things multiplied together. This is going to equal the sum of two logs, the sum of two logs. Same thing with the quotient rule. Notice I'm taking the log of a single quotient. This is going to equal the difference of two logs. And then last, expanding and condensing rule, when you have the log of something raised to a power, you're allowed to bring that power out front, and this is going to be your logarithm times your power. And this right here just shows you another table of the exact same thing, but it kind of shows you the relationship between the exponential rules and the log rules. So it's kind of neat. Here, when you're multiplying like bases, you add the powers. Here, when you're taking the log of two things multiplied together, you're adding your two logs. One thing I might mention, because I'm probably going to end up saying this at some point, a log is a power. A log is a power. And so it's kind of easy to see it here because I'm adding my powers. Well, here I'm adding my two logs. And since a log is a power, I'm adding my two powers. So that's just something that might be helpful in the future. All right, now let's use these properties and we're going to rewrite the logarithms. So notice that my overall operation is a quotient. Okay, so I'm taking the logarithm of a quotient. So what I want to do then is I want to use my quotient rule, and I want to have the log of my top guy minus the log of my bottom guy. So let's write that first. So this is going to equal log base z, don't forget about that, of the top guy. Well, the top guy is x to the 5th y cubed minus log base z of the bottom guy, which is just a 3. Now ask yourself, am I taking the log of a product or a quotient or a power here? And the answer is yes, I'm taking the log of a product because this is the log of this guy times this guy. So then let's use our product rule for that. So that'll be log base z. Remember, the product rule says that when you take the log of a product, it's going to be a log plus a log. So let's take the log of the first guy, x to the 5th, plus log of the second guy, y cubed. Minus, now on this guy, I'm not taking the log of a product, and I'm not taking the log of a quotient, and I'm not taking the log of a power. So I know that this guy here is finished. I'm just going to copy him down. Let's go back to the beginning. So ask yourself again, in this first term, am I taking the log of a power? Am I taking the log of a product? Am I taking the log of a quotient? If your answer is yes to any of those three questions, then you need to keep on going. And we are taking the log of a power. So notice this is x to the 5th power. So let's use the power rule. So the power rule says that we're going to take that 5th power and we're going to take it out to the front. So this will be 5 times log base z of x. When we go to the second term, we ask the same question. Am I taking a product, the log of a product, the log of a quotient, or the log of a power? And it's a power. So we're going to take that 3 out to the front. And we're going to multiply times the log base z of y. We already know that that third term is finished, so we don't have to do anything to it. All right, and then I know I'm finished. So let's do the same thing for number 22. On this one though, let's that root there is kind of messy. So let's use what we did in the last class and let's change our root into a fraction power before we do anything with log rules. So we have log base p of this fraction m to the 5th over k times t squared. And since this is a cubed root, we're going to raise this to the 1/3 power. So now look at the overall operation and ask yourself, am I taking the log of a product, a quotient, or a power? And we would say that the overall operation is a power. So let's use our power rule. So that power is going to come out to the front. So this is going to be log base p, but we're going to move our power out to the front times 1/3 of the fraction m to the 5th divided by k times t squared. Ask the question again. Am I taking the log of a product? Am I taking the log of a quotient? Am I taking the log of a power? And so we're taking the log of a quotient. So we'll use the quotient rule. Now remember that the quotient rule says we're going to take this log and we're going to split it into 2 logs, and those 2 logs are going to be subtracting, one subtracted from the other. So since I'm going to split this into 2 logs, the 1/3 out in the front needs to go to both of those logs. And so I'll just put these 2 logs in a bracket so that I can pass the 1/3 out later. So we have log base p of the top, n to the 5th. There's the log of the top, minus log base p of the bottom, which is k times t squared. Okay, so there's my splitting of 2 logs. All right, so we've got our 1/3. Let's look at the first term. Do I have a power, a quotient, or a product? And I do have a power, so let's use the power rule on that piece. Power rule says I have 5 times log base p of m. Now, when I look at that one, this guy is totally finished. I have no more powers. I have no more products. I have no quotients. So that term is finished. Let's go on to the next term. My next term is the log of a product. 2 things multiplied together. I've got k multiplied by t squared. All right, so we're going to have to split this guy into 2 logs. Don't forget though that I have a subtraction out here, and that subtraction needs to go to both of those logs. So I'm going to go ahead and distribute that subtraction to both logs. So this will be log base p of the first factor, k. Normally, because this is product, I would have plus, but remember, I'm going to pass out, I'm going to distribute that negative. So this is going to be minus log base p of t squared. I'm almost finished. There's 2 more things that I need to do. One thing that I want to do is I want to take care of my power, so we'll pass it to the front of this. And the other thing that I want to do is I want to take my 1/3 and I want to pass it to all 3 pieces. So I'm going to do both of those at the same time. So when you take 1/3 times 5, that'll be 5/3. Log base p of m. Once again, notice that the log and the m are the same size in the font. Minus, take your 1/3 times log base p of k, minus, now I've got 1/3, but don't forget we've got a 2 that's going to come to the front of that, so it's actually a 1/3 times 2. So this is going to be 2/3 log base P of T. And now that is completely expanded. And for the record, folks, did I write? No, I didn't say I said rewrite, but I didn't say we would be expanding. So often this is the word that will go with this section because we took our logs and we expanded them out. All right, now let's go to number 23 when it says use the properties to rewrite logs as a single log. So these we're going backwards. Single log says we're going to condense down to a single log. All right, so when you look at the first piece, let's follow what's in the group. And in the group, we have a log minus a log. Well, that looks a whole lot like, let's go back to our properties really quickly. Log minus log looks like this guy. It looks like the right side of the property. So what we're going to do is we're going to write down the left side of the property. So this is going to be log base, that's a B, log base B of K over M, using my quotient rule, minus log base B of A. And again, I have another quotient. I have a log minus a log. So this is a quotient. So this is going to turn into log base B of K over M over A. Now remember, this is an A over 1. Now you don't want to leave it like that. Let's go ahead and clean that up. We'll multiply by the reciprocal. So this is going to be log base B of K over M times the reciprocal 1 over A. And then when I multiply the numerators and multiply the denominators, I'll have, and this is my final answer, log base B of K over, K over M times A. Single logarithm. I've condensed it down to a single logarithm. And I think we have one more here. Now you'll notice that I have a log minus, it's not log minus log, it's log minus a half of a log. So the first thing I need to do is I need to take care of this half. So again, let's go back to our rules. And this looks a whole lot like this guy right here, where I have a number multiplied out in front. So let's rewrite it using this, and we'll take our 1/2 that's out front and we'll make it back into a power. So that'll be the first thing. So copy down the first term, log base B of 2y plus 5, minus the half is going to be a power over here. So this is going to be log base B of y plus 3, that quantity raised to the half power. You could write that as a square root if you wanted to. Now I have log minus log. So now I can use my quotient rule. So the quotient rule says that I have a single log of a quotient, a top and a bottom. So on top I have 2y plus 5, and on bottom I have y plus 3 quantity to the 1/2. I've condensed it to my single log, and folks, this is okay to leave it like this. I know I have a square root on the bottom, but it's totally fine to leave it just as is. All right, so that wraps up 6.3. This right here, change of base rule, this is mostly for calculator use, so you can take a look at that. And we don't use it a whole lot, but my lab might use it a little bit, so it's a good thing to take a look at it. Hey guys, so this is going to be the section 6.4 video. This one's going to be a really quick one, kind of like your notes video was also really quick. So the first thing is to just go over the embedded questions that you had in this particular section. And so I walked you through in the video sketching the inverse. Remember that those 5 interesting facts that we did earlier in this chapter back in section 6.1 about how to get the inverse, all I have to do is trade the X and the Y values. So that's part of what we're doing here. And so it says we've already labeled and everything, so we've graphed it. And so now what you are required to do for the embedded question is to get the domain and the range. and find increasing and decreasing, and then the equation of that vertical asymptote. So let's go ahead and we'll uncover these, and then we'll do the one question that we have. So my domain is from 0 to infinity. Now remember here that I'm only looking at the hand-drawn graph. This is the logarithm graph. Up here, this is the exponential graph, and we've already walked through the exponential graph earlier in this chapter. That was one of our new parents. This is the logarithm parent. So I'm only looking at this piece when I'm getting my domain and my range. So my range then is going to be from negative infinity to positive infinity. We're going from the bottom, it goes down forever and ever, and we're going all the way up to the top. It goes up forever and ever. It goes slowly up forever and ever, but it does go up forever and ever. And then it asks for the increasing and decreasing. We'll notice that this handwritten piece of the graph is always increasing. And so it's increasing from my vertical asymptote, which is at 0, all the way to infinity. Oops, I uncovered the wrong one there. So it's increasing from 0 to infinity. And then that vertical asymptote is at x equals 0. So that's the embedded question points that you could have earned for today. All right, now let's take a look. I'm only being asked to graph another parent. Now this guy over here, this was the parent that had a base of 4. This guy is the parent that has a base of 10, because remember, when you have no base, it's an automatic base 10. So this is my common log that I'm graphing the parent of. And so a couple of special things. When I ask you to graph the parent, the vertical asymptote on the parent is always going to be on the y-axis. So my vertical asymptote then is at x equals 0. My special coordinate, remember back with exponentials, the special coordinate was at 0, 1. It was up on the y-axis. Well, when you trade the x and the y values, this is going to be at 1, 0. So my special coordinate is going to be at 1, 0. And remember also how, let me go back to this. Remember how also back in the exponential parent, we always had that special coordinate 1, and then whatever the base was. Well, now on logarithms, my special coordinate is going to be whatever the base is, comma, 1. So in this particular case, we're going to have the special coordinate 10, 1, because my base is 10. Now, I don't even know if I have 10 blocks, so let's take a look. 1, 2, 3, 4, 5, 6, 7, 8. No, I don't have 10 blocks. But you can probably have, I'm going to stretch out my 1 here. You can probably have the margin of your paper. And so I'm just going to go up. I'm not going to quite reach it because I just haven't gotten up that far yet. And then for the bottom, we're always going to get closer and closer and closer to our vertical asymptote. And so that's going to be the parent for the common log. Again, it looks very similar to the parent for this guy, which had, it was a log with a base of 4. This one has a base of 10. Same exact concept.